In the last lecture, we saw regression problems. In this one, we're going to start looking at classification. So I'm going to talk a bit about the difference between regression and classification problems. These are all supervised learning problems, but they have different goals and so different requirements for the models. And then we're going to take a look at logistic regression, which, even though it is regression in a sense, it tries to predict the probability of belonging to a class. It's actually a classifier because we use it to split the data into different subgroups. And we're also going to revisit that idea of using transformations, nonlinear transformations, to increase the power of our models. And now we'll face the problem of overfitting, and we're going to see how we can handle this specifically with this technique of cross-validation, although I'm going to explain some simplified approaches first. So let's start with this problem of separating classes of examples. In regression, we use that example of the straight line. For instance, the first example that we saw, we defined this class of hypotheses, a set of all straight lines. We decided to use that one, and we created this model which allows us to specify any straight line given these two parameters, the slope and the intercept here. And now we try to approximate this as much as possible to the data that we had. But in classification, we do not just need a single line. We need to know, even if we draw a line separating classes, we need to know which side of the line corresponds to each class. So if we generalize this for a linear model in n dimensions, this would be a hyperplane. So it would be a line in 2 dimensions, a plane in 3 dimensions, and then you could have the equivalent in 4 or 5 dimensions and so on. And we need to know to distinguish between one side and the other. So what we can do is we can define the plane that separates the classes using a vector that is perpendicular to the plane. And now at the plane, we have this equation here. So if we multiply this vector that is perpendicular to the plane with the coordinates of any single point, and then add this constant that determines whether the plane is higher or lower, this inner product here will be plus this constant will be 0 when the point lies at the plane. This expression will be positive on one side and negative on the other. So this x here is a n-dimensional vector with the features of our examples. So this would be something like this. We have this by adjusting these parameters. This vector w here is the vector perpendicular to the plane. And then we have a constant here that determines if the plane is higher or lower. And this expression is equal to 0 for any point that lies on this plane. If a point lies on the one side of the plane, this expression will be positive. It will be larger than 0. On the other side of the plane, it will be negative. So using this expression, we can separate the space into two subspaces, one on one side of the plane and the other on the other. So this allows us to separate the two classes using this linear model. So the linear discriminant will be the separation between the two subspaces, the plane, but we can obtain this function that will be positive on one side and negative on the other, and so we can assign different classes depending on where the point lies. Now the problem, of course, is the same as we saw in the previous lecture. How do we find the actual parameters for the model? So this would be our model. We are creating here a model with parameters that allows us to span all the hypothesis class, which should be the set of hyperplanes, but we need to select the specific one to separate our data. And now that would be the problem here, which is a similar problem, analogous problem to what we solved with least mean squares minimization for regression, but now we have a different type of model with a different goal. So let's look at logistic regression. The reason why it's called a regression is because we are assuming that there is some function that we can find that gives us the probability of any example given by this features coordinate vector belonging to class 1. So let's say we have class 1 and class 0, and we want to compute the probability of belonging to class 1. The probability of belonging to class 0 will be 1 minus the probability of belonging to class 1, and we want to separate the set of points at the hyperplane where the two probabilities are the same. That is, we can imagine that on one side the probability of belonging to class 1 is higher, on the other side the probability of belonging to class 0 is higher, but exactly where the two are the same, we want to cut and separate the two parts. So this is a regression because we're actually trying to adjust the function to a continuous value, which is the probability of belonging to the class. So in that sense, in the inner workings of logistic regression, it's a regression. But we are going to use it as a classifier to produce this hyperplane where we separate the two classes at the plane where the probabilities are the same. So we are going to use this relation here. So when at the position of the plane where we will place the plane, the logarithm of the proportion, the probability of belonging to class 1 and 1 minus the probability of belonging to class 1, which is the probability of belonging to class 0, will be 0 because this will be 0.5 and this will be 0.5 here below at the position we want the plane to be placed. If we go on one side, we will have this, for example, on the side of class 1, this probability will be higher, 1 minus that probability will be lower, and the logarithm will be positive. If we are on the other side, the reverse happens and the logarithm will be negative. So basically, since we are approximating this probability with our function, we are assuming that we can use this function for this. We can compute this, and this will give us the same idea that we want here, which is negative on one side, positive on the other. Furthermore, we want this to be a linear separation. So this would be our inductive bias. We're going to use only linear classifier in this case, and this will be a linear separation. So we can do this. We can try to find the parameters for the hyperplane such that the logarithm of our probability estimate, which uses the same parameters, over 1 minus the estimated probability of belonging to class 1, will give us the same result as this expression here, which is the expression that is positive on one side of the hyperplane, negative on the other, and 0 when we are exactly between the two classes. So this way, we are restricting everything to a linear classification. We are determining a hyperplane here, and one that follows the same property that we get from our function when we are trying to predict the probabilities. So basically, solving for this, we obtain this form, this shape for our function with the parameters there that we can optimize. So this will be what we're going to try to approximate, use the function we're going to use to approximate the probability of belonging to class 0 and class 1. And it will have this property that it will separate the two classes in a hyperplane. So this is what the function looks like. This is the logistic function, so that's why it's called the logistic regression. It grows from 0 to 1, so it can be used to model, to estimate some probabilities. And it has this nice shape because if we go outside the range of this function on one side or the other, it will level off and have always the same value here. So it changes at the region between the two classes, and then everything on this side belongs to one class and everything on this side belongs to the other. So now again, we're going to use maximum likelihood to optimize the parameters, exactly like we did with regression. Only now, since the functions are different, the equations are different, but the idea is the same. So the likelihood of our parameters given some set of data is the probability of having that data, assuming our parameters are correct. And we can do this by taking the product of all the classes of our points, using our function, the predicted probability, when the point belongs to class 1, or 1 minus the probability when point belongs to class 0. So note that if the point belongs to class 1, 1 minus 1 is 0, and this part is raised to 0, so it will count as 1, and it will not make a difference. If the point belongs to class 0, this gn raised to 0 will count as 1, and we'll only use this part here. So basically what we're doing here is the product of the estimated probability of a point belonging to class 1 if the point belongs to class 1, or 1 minus the estimated probability of belonging to class 1 if the point does not belong to class 1. And the product of this is the joint probability of all of these points in our sample. So now we want to adjust these w's. Remember that the w's affect here our probability estimate, so the G function, and we want to adjust this so that we maximize the probability of the data. We can take the logarithm of this. It's more practical than doing all of this product. So this converts into a sum. We have the logarithms there. The exponents come down in multiplication. And basically, this is what we need to maximize. And this ends up being the same as minimizing the symmetric of this, which is the logistic loss or cross entropy. And so this is the expression that we want to minimize in order to adjust the parameters of our G function so that we maximize the likelihood of those parameters. Okay, so let's see an example with a linearly separable set of points. So a set of points with different classes. The classes are linearly separable if we can draw a straight line and separate the two. And we can, if we wanted to implement logistic regression, we could, for example, write an auxiliary function just for the logistic function. So this is the logistic function here. This is just the writing in Python that part. So e raised to minus 1 times x plus 1, and then 1 over that denominator. And now we need to minimize this logistic loss here, which is the class multiplied by the logarithm of the probability, and 1 minus the class multiplied by the logarithm of 1 minus the probability. So note that this can be 0 or 1, and if this is 1, we are using this term here. If it's 0, then we'll be using this term here. So what we can do to implement this is separate this into two parts, and we compute the logarithm multiplied by the class, and the logarithm of 1 minus the probabilities multiplied by 1 minus the class, and then just add the two. And this is the probabilities estimated are the result from the logistic function there. So basically what we need to do is to pack this into a loss function that we can fit in with minimize, as we saw previously. And so this will receive a vector with the parameters that we need to adjust, and then whatever data we need. So in this case, it's the features and the classes for our examples. So the coefficients here will be for the inner product will be those in all of these rows and the first column here in the theta. So this is the W, and we use these coefficients for multiplying with the features of our examples. So basically what we're doing this is this inner product here, and we are then computing the logarithms of the probabilities and creating the loss function. So this would be if we wanted to create the loss function and the logistic function in order to use minimize, as we did previously with fitting models in general, and then we would get this result here. But this is just to illustrate the basic idea of logistic regressions. Actually, we're going to use an implementation of logistic regression that is already present in the scikit-learn library, so we are not going to worry about implementing the code at this level, because there are lots of numerical optimizations in these algorithms, and so our own implementation will probably be too simplified to actually work well in practice. So let's see what happens if we have a set of data in which the classes cannot be separated by a straight line. So suppose that we have this. In this case, this is an example of data from tumor cells and normal cells, and the features here are the activity of these genes. So an actin binding protein and a calcium binding protein here, and we have the activities of these genes. If we plot them, we can see that there is a difference between tumor cells and normal cells. However, the frontier between the two is not linear, so we cannot draw a straight line and perfectly classify all of them, because we have this example here going a bit towards the red side. So in this case, we cannot, using a linear model in this data set, we cannot solve the problem of classifying them correctly. But let's use the same trick, and this is a basic idea that is important. We can do some transformation on the data. For example, we can expand it to higher dimensions, and as long as the transformation is not linear, we can then use a linear model in higher dimensions and mitigate our problem, or even succeed at classifying correctly. So let's add a term that is the product of these two features. So we have the activity of one gene, the activity of another gene, and now we add a third term that is the product of the two. This is a non-linear transformation. We are multiplying the two, not multiplying by a constant, but multiplying the two features. And this can easily be done by creating a new matrix, which has the same number of rows and one more column than the matrix that we had originally. And now we copy the original matrix to all the columns except the last one. And for the last column, we put the product of the first two. So now we have a matrix with all our data, with the new features expanded. So what we would do here would be, we would load the data, we would standardize it. I'm going to talk a bit about that later in this lecture, but basically do all the pre-processing that we would need, and then we added an additional feature, so that we would transform the data from 2 dimensions to 3 dimensions using a nonlinear transformation. Okay, so this is the idea. We have the original activations here, the gene activities on this plane here, and we add a third coordinate, which is the product of these two. And since it's the product of these two, now the points are all spread out in this curved surface here. And now we do a linear classification, so we do logistic regression in 3 dimensions, using 3 features and creating this plane that tries to cut between the two classes. But since our transformation was non-linear and now the points are spread out in the curved surface, when we cut with this plane, even though the plane is straight, the intersection with this curved surface where all the points are spread out is a line. So if we project this back to the original space for the classification, we actually get something that is curved, separating the 2 sets of points. Now, we're not going to do this with our implementation of logistic regression, because that would not be very efficient. We're going to use the logistic regression class from scikit-learn. So this is implemented and optimized and we can, to use these classifiers in scikit-learn, what we do is we create an object from this class. So basically we call the class constructor. There are some parameters here. This is a regularization term C, which I'm going to talk about next week if I have time. But basically we are going to turn off regularization by giving a very large value for C. So this does not use regularization. The idea of regularization is trying to change a bit the way the model is being adjusted, the parameters are being adjusted to avoid overfitting. But we are not going to worry about this now, so just leave this value very high, because the default is 1 and it's strongly regularized. And this tolerance factor here is just a value for the optimization algorithm when it decides to stop. So the lower you have here, the more precise will be the result at the end, or the more accurate will be the result at the end, because it will do more iterations and only stop when it has a very low change from one iteration to the other. So this is, we get an object that computes the logistic regression, and now we fit it by calling the fit method, and giving it the matrix with the features, and then a vector with the classes. Now, depending on how we loaded the table, this could be just a vector with the class labels, or if you have this in a matrix, you can specify that you just want the vector with the class labels. So this allows us to adjust the parameters of the logistic regression, do the fit, and if we do this in the expanded data, we now have something that is curved in the original space, because we did a nonlinear transformation on the data. And we can increase the expansions. For example, we can add not only the product of the two, but each of them squared, and now we are doing this classification in 5 dimensions with this nonlinear transformation, and when we project it back to the original space, we get this separation between the classes, and so on. We can increase the number of features by doing this kind of nonlinear expansions. Of course, there is a problem. If we overdo it, we get some strange things. For example, here our classifier is saying that a point there will be considered a tumor, and there does not seem to be any reason for that. So this is that problem that we saw previously of overfitting. Okay. So what can we do to try to prevent this? The first thing that we need to do is to have some quantitative measure of the performance of our models. In this case, it would be a classifier, but we could also consider the case of regression, and use that to estimate how good or bad the model is performing. So for regression, we used the sum of the squared distances. Sometimes we can use RMSD, which is the root of the mean squared distances. We can take the average of this over all the points, and then compute the squared root of that, so that we are back in the same units in which we are computing the regression. But this would be an intuitive measure for regression. With logistic regression, we are minimizing this function, the logistic loss, but this does not give us a very intuitive result, a very useful result, and also it's hard to compare then with other classifiers if we use other classifiers and so on. So what we can do for classifiers is try to find a more general approach to evaluating the performance. And we can start by looking at a confusion matrix for binary classifiers, which is a matrix that is going to tell us where the classifier is getting right or wrong. So this would be the prediction of our classifier. Our classifier is predicting class 1 or class 0, and this is the actual class of our examples, class 1 or class 0. So, or positive and negative if you want. A true positive will be an example that is predicted to be in class 1 and belongs to class 1. So our classifier is telling us it's a positive example, and it actually is. So it's true that it's a positive example. A false positive is one where the classifier is telling us it's positive, but it's actually a negative example. It belongs to class 0. So this will be falsely classified as positive. The true negative is class 0, and the false negative is one that is actually positive, but our classifier is saying is negative. So if we count how many of each different case occurs, we have all the correct predictions here on the diagonal and different kinds of errors of the diagonal. So now we can use that for some indices, for some performance measures. Accuracy is basically the fraction of correctly classified examples. So we sum the true positives and the true negatives, and we divide by the total number of examples, and this is accuracy. If you have an accuracy of 0.9, it means that the classifier is getting things right 90% of the time. Now, there is a difference here sometimes in whether we want to find all the positive cases, or we want to be very confident when our model says something is positive. And this can be measured differently in precision and recall. So precision is the fraction of true positives that we have in all the examples our model is telling us are positive. So if precision is high, it means that when our model says some, or when the hypothesis that we find at the end, when our classifier tells us that an example is positive, then we can be very confident that the example is positive. We have a very precise classifier in that sense. But our classifier may be missing a lot of positive examples. It may very rarely tell us that something is positive. When it does, it really is positive, but there are many cases where examples are positive and the classifier is giving us false negatives. False negatives do not matter for precision. So another thing that we can think about is how many of the positives are we getting from our classifier. So this would be the fraction of true positives, the one that are positive and our classifier is telling us is positive, and the total number of positives in the data set. So the ones that our classifier is getting right and telling us are positive, plus the ones our classifier is getting wrong and telling us are negative, but falsely, because they are actually positive. So precision and recall are measuring two opposite things. The fraction of true positives in everything the classifier tells us is positive, that's precision, or the fraction of two positives in everything the classifier should be telling us is positive, so all the real positives, and this is recall. And one common indicator or measure of performance also used is the F1 score, which is the harmonic mean between precision and recall. So you can compute it in different ways, but basically it tries to join the two of them together in a harmonic mean to combine them in a single score. We are going to look here at accuracy. So accuracy is very intuitive, easy to understand. It's the fraction of correctly classified examples, and that's the measure we're going to use here. But I just wanted to briefly mention these ones so that you know what are these other common performance measures for classifiers. So let's look at the errors that we're going to find and how we can use this to solve the problem of overfitting, of using models that are too powerful for the data that we have. So we have this objective here. We are trying to find a function that does some mapping between the features and whatever target values we want to predict. In a regression, it would be a continuous value. In a classification, it would be a class label. But in general, this is what we want to do. We have a training set in which we know the correct target values. So this is not really the set where we want our final hypothesis to work well, because we don't need to predict the values here, we already know them. What we want is to predict the target values for any example that we may meet in the future drawn from the universe at random And those are the ones that interest us because that's where the predictions will matter. We can measure the training error because we can measure the error on this training set because we have the correct target values there. But the problem that we saw previously is that the training error is not a good indicator of how well our hypothesis will perform in the whole universe of examples, because we are purposefully trying to minimize the error in the training set. So this means that we are adjusting the parameters to minimize this particular error measure, and that can lead to overfitting because we choose a hypothesis that is too much adjusted to the training set and then doesn't work well outside the training set. So this would be the solution. We can monitor error outside the training set using another set of data that is not being used to optimize the parameters. And this could be an estimate of the true error, which will be the error on average on the whole universe of data. So let's see an example here. We can split the data into a training set and a test set. We use the training set to adjust the curve. For example, going back to the regression model, because it's very simple to visualize, we use these blue points to compute this polynomial of degree 5. And now we can evaluate the error on the test set. So the test error will be evaluated on this set of red points that was not used for training. It's just to get a measure of the error outside the training set, and this gives us an estimate of the true error. Note that the true error will be the average error over the whole universe, and we cannot really measure that, but we can estimate it using the test error. One important thing here is that these estimates will depend on how the split was done. So depending on which of these points end up in the training set and in the test set, we will have slightly different curves and slightly different test errors because we are using different points. So we can imagine that whenever we do this, whenever we split the training set or the data that we have at random in the training and test set and then fit and measure the error, we obtain slightly different hypotheses at the end. The curves are not the same, and slightly different error measures in the test set. All of these are estimates of the true error, but they are not a measure of the true error. They are measured on the test set, but not on the whole universe. However, this is an unbiased estimate, which means that if we do this infinitely, we have this distribution, but if we do this an infinite number of times and take the mean, it will correspond to the true error in this particular case. Okay, so this is unbiased because it's not tending. Basically, the mean converges to the actual value we're trying to estimate. So we can consider these two measurable errors so far. The training error, which is the error measured on the data that we are using to fit the parameters. This is very biased because we are adjusting everything to minimize this particular error. And then the test error, which is measured outside the training data and is used to estimate the true error. And this gives us an unbiased estimate of the true error because we are not doing anything with this test error. We are not choosing anything based on that value. Now, there are some errors that we cannot actually measure. The true error is the average or the expected error for all the universe. We cannot measure that because we don't have the whole universe of points. And the generalization error will be the difference between the true error and the training error. So, and this is something that we cannot measure also. Okay, so how can we use this to solve the overfitting problem? We saw, for example, with regression using those polynomials, that the increase in the power of these models, so using polynomials of higher degree, allows us to fit increasingly better the curve to the training data. But then we start having these problems here of doing predictions that do not make much sense. So what can we do? We could use a part of the data, leave out a part of the data outside the training set to monitor these errors. And what we would get would be something like this. As we increase the degree of the polynomial, in this case, the error on the data that we are using to fit the curve is going down because we are going closer and closer to all the points. But at some point, the error outside the training set will start going up because we start having these kinds of wild predictions that do not match the data. So we can look at this and see basically three different parts of this graph. In this part, we see that the problem, both in test and training, both errors are high. So this occurs because the model cannot fit the data adequately. We have something that is, for example, a straight line. It cannot accompany the pattern of the data. And so the training error and the test error are both high. And this situation is called underfitting. Our model cannot properly represent or adjust to the data. If we are on the other extreme of the graph, what we can see is that although the training error is very low, there is a very large test error. So there is a very big difference between training and error and the training and test error, and the test error is increasing in this case. So this is a characteristic of overfitting. Our model is adjusting very well to the data, but actually it's adjusting too well to details that do not generalize, and so it ends up making more mistakes outside the training set. This could be something like this, where we have huge values over here, so there's a lot of error in this prediction. There are strange effects like this, and so on. So here we can have a very low training error, but a much higher test error. And so we can see this problem. Basically, when we are overfitting, we are increasing the generalization error, but especially important, it means that we are increasing the test error here. So it would not be a good idea to choose a model that performs like this, because even though it's very good on the training set, it works bad outside the training set. So let's see how we can select the models. We see that they are not all, they do not perform all the same, and there is here one where we can see the test error is lower than everything else. So intuitively, this would be the best model here. A degree 5 polynomial, in this case, would be the ideal choice because it's the one that has the lowest error outside the training set. And this is how we can choose which model to use. We're going to look outside the training set and choose the one with the lowest error there, because each of these individual points here is an unbiased estimate of the true error for the hypothesis we got for each of these models. And so we choose this one as the best hypothesis of the set that we have here. Now, one problem with this is that when we choose the lowest test error, then this is no longer really a test error because we are making a choice. And this is a problem that results from choosing based on that value. So imagine that we are rolling dice and have this distribution. So this is the distribution from which we can sample some value. But what we do is that we take a sample of 10 and then choose the smallest one, and then do the same thing and the same thing again and again and again. And now the distribution becomes very different, because since we are taking out 10 at a time and choosing the smallest one, we end up on average getting something that is smaller than what we would have if we just took the average of all the examples we are taking. So even though each of these points is an unbiased estimate of the true error for each of these hypotheses that we got here, if we take all of them together and pick the smallest one on purpose, now this becomes biased, because as we repeat this, we have a much higher probability of choosing some test error that ended up being less than the true error by chance, because this is a random sample, than one which is higher. And so we are biasing everything to underestimating the true error. So basically, we cannot really do this and call it the test error, because the test error must be an unbiased estimate of the true error. What we are doing here is a validation, and this is the solution. Basically, we need to separate things into three sets. We have the training set, which we use to fit the parameters and choose the best hypothesis. This is the one that we use to train the model. And now we need a validation set in order to select other things. For example, which model are we going to use? A polynomial of degree 1, 2, 3, and so on. We need to check outside the training set. So we need to do this here. But this is not the test set. This will be the validation set, because it's outside the training set, but it's something that we are using to choose. And so we are biasing that estimate. And the test set is left out and is only used to estimate the true error when we have everything done. Now, one problem of using this simplified scheme, this is done in very complex models like deep neural networks and things like that, but usually we avoid this simplified scheme, because the problem is that we are deciding everything on a single hypothesis. Each of these points here corresponds to a single hypothesis obtained when fitting the model of degree 1, fitting the model of degree 2, and so on. And now we are choosing this on a single hypothesis, even though this is just a sample from many possibilities. It depends on how the train and the validation set were split. So one improvement of this is cross-validation. In cross-validation, we are trying to overcome the limitations of this sampling, where looking only at one hypothesis may tell us something that would be different if the split was slightly different. And we can mitigate this by taking several of these hypotheses and averaging. And this is the idea of cross-validation. We can start by leaving out the test set. We are not going to use that for anything except at the end for estimating the true error. But the training set, we are going to split into a number of folds, for example, 5 or 10 k folds. And we're going to leave iteratively one of these folds out, train with the other k-1 folds, average the validation error and the training error there, and then repeat this by leaving another fold out. So now we are taking a sample of different hypotheses obtained using different training sets, averaging that, and this will give us an idea, a better estimate of how this model will behave when we train it with this kind of data. So let's look at this graphically, considering the classification problem that we saw earlier. So those two genes and the classifying with logistic regression using some expansion of the data so that we can have these curves. Now this is the training set, a set of red and blue points. We split this into 5 folds. And at the first iteration, we leave this part out. So these are the larger points here for validation. And we adjust this classifier only to the smaller points here. So the ones that are represented as smaller dots. And now we measure the training and validation error for when we leave this fold for validation. And now we do the same thing with the next fold. We train with all of these, but we leave out this block here for measuring the validation error. And now we repeat and repeat and repeat, and we do this for all the 5 folds. So now we have 5 different hypotheses, 5 slightly different curves here. You can see them changing. And they have different training errors and different validation errors, depending on which points were left in the training set and which points were left outside for validation. So now we can average this and have a better idea of how this model will perform when we adjust it to this kind of data. So we have different hypotheses here, but on average, it gives us a better idea of the model's performance. So with training and validation, we are estimating the true error of a single hypothesis and then use these point estimates to try to get the best, for example, to select the best model or something like that. We actually select immediately the best hypothesis. When we are using cross-validation, we are averaging the estimates of the true error for several hypotheses in the same model. And this average gives us a better estimate for that model, for how that model will generally perform on this data. It does not give us the estimate of any specific hypothesis, and we then have to train the model again in order to find the best hypothesis. But cross-validation tends to perform better than simply splitting into training and validation. So let's see an example. We want to find the best model for classifying these data here. And we're going to start by loading the data. We can use this load.txt function from NumPy. This just loads everything into a NumPy array. And we are going to do some pre-processing. Now, there are two steps here that are important. One is shuffling the data, because we don't know how the data is sorted in our file. And it could be, for example, all the red points first and all the blue points later and so on. And so when we start splitting into folds and such, this could be really messy. So we can start by shuffling the data. You can use the shuffle method in scikit-learn util, so this function. And what this does is, if you give it an array, it will shuffle it on the first dimension, on the rows, and return a copy of that array that is randomly shuffled. So this data matrix now has all randomized order on the examples that we read. Another thing that is important to do is to rescale the data so that all the measures are on the same scale. This, in some cases, for example, with logistic regression, since it's a linear classifier, if you're just using the original data, it will not be a problem. But in general, it is. There are lots of different models where this can be problematic, like support vector machines or neural networks and so on. And it's always a good idea to deal with data that is around the same scale, because that gives you a better intuition about the error values, the regularization parameters and such. So two usual ways of rescaling the values will be normalization, where we put everything on a scale between 0 and 1 by subtracting the minimum and dividing by the range for each individual feature. So all the features will be rescaled to be between 0 and 1. Or standardization. Standardization is less sensitive to outliers, and what you do is for each feature, you subtract the average and divide by the standard deviation. So it means that everything will be centered at 0 with a distribution that is mostly between -1 and 1, with perhaps a few outliers, but around that range. Now, this is important to do because sometimes you have features that represent very different things. You can have, for example, income and age and height and things like that, which are in very different units, years, euros, centimeters, and you cannot really compare them at those scales. So we can rescale everything to be at the same range. And an important thing is to store these parameters, because we will have to apply the same rescaling operation for new examples that we may want to feed into our classifier in order to predict the class. Okay, so if you're doing this in a real application, you need to store these rescaling parameters. But the idea here is just to basically change the units of measuring so that all of the features are on the same scale. Now, we're going to select the best model by expanding the data. Logistic regression is a linear classifier. We only have two features, x and y here, two features, x1 and x2, which are the coordinates of the points. And it's obvious that we cannot separate the two classes with a straight line. So we need to do this with logistic regression, we will need to expand the data with nonlinear transformations, and we're going to do this polynomial expansion. So the product of the two the first one squared, the second one squared, the first one cubed, the second one cubed, the product of the square of one with the other, and so forth. So we can do this kind of expansion in order to have different models, different logistic regressions at different dimensions. Now, one important thing to note is that this is just to illustrate the idea, because we are looking at these basic concepts of model, fitting the hypothesis, measuring the overfitting, increasing the power of the classifier, and so on. And this is something that you can do to illustrate and to understand the approach. But in practice, if you actually need to do something like this, you will not do it by hand with logistic regression. You will do something, for example, using support vector machines that do these kinds of expansion implicitly with some numerical tricks, the kernel trick in the case of support vector machines, or artificial neural networks that learn how to do the appropriate nonlinear transformations on the data. So in a practical application, you would use more powerful models like this that would automatically do these transformations. We are doing this manually with logistic regression because we want to focus on this idea that then is used by other models in a more implicit way. But it's important to understand this idea that we can use the same kind of linear classifier after transforming the data, and that will increase the power of classification. The same as we did for regression. Okay, so now we can expand the features. Let's say using this function here, we have a large matrix with lots of new features here, and now we can separate this into train and test set. So if you want, you can use the train test split on the model selection module of scikit-learn, and for this you give the features matrix, the class labels, you specify what fraction to reserve to the test set. In this case, we're going to leave out 1/3 for testing, and you can also do a stratified split. So what this does is you give the class labels to the stratify argument, and the train test split will now guarantee as much as possible that the proportion of the different classes in the test set will be the same as it is in the training set. So this helps prevent one problem, that by chance, suppose that you have lots of red points on the test set and then lots more blue points on the training set, and things would not work very well. So this allows you to guarantee that there is a balance between them, so that the proportions of the classes on the test set are as close as possible to the proportion of the classes on the training set. Okay, so now let's do cross-validation. One easy way of doing cross-validation with scikit-learn is to use this k-fold class that will give you iteratively the indexes for the training and validation set when you loop through the split iterator of the k-fold class. So the way this works is, suppose that you have a vector of points. It doesn't matter. It can be a matrix or a vector, because what split will use will be just the first dimension of the array. And in this case, suppose that we have these 12 points here with different values. What we obtain when we say we want to split in 4 folds, in this case, we create this k-fold object, and now we have 4 iterations of this loop. And in the first iteration, the first fold is left out, so indexes 0, 1, 2 are left outside, corresponding to these 3 points here, and the others are left for training. So this would be the training indexes and the validation indexes here. And now on the second iteration, it's the second fold that is left out. So index is 3, 4, 5, and we have the rest for training. And so on, the third iteration, the fourth iteration. So what this does is automatically select the indexes along the data set, so that we can easily find the points for training and for validation. And that way we can implement this. So we can create a function that receives the whole matrix with all the expanded features, the corresponding class labels, the indexes that are going to be used for training, and the indexes that are going to be used for validation. We don't need that additional argument because I already put that here. So this tells us what is the data, for the features, the labels, and the indexes for training and validation. This argument here tells us how many features we're going to use, so that we can use only the 2 original ones, or 3 with 1 expansion, 4, 5, and so on. And now we're going to create a logistic regression classifier. This is that regularization term I mentioned early. We are going to switch off regularization by giving a very large number here. This is just for the numerical optimization. You can leave it like that. But what we're going to do is adjust the classifier using only the training examples. So from the features matrix X, we are going to use these examples in the training indexes and only this number of features that is specified there. And we are going to fit the classifier by feeding in the same, the corresponding classes. So we are going to use also the training indexes for the corresponding classes. After the classifier is trained, we're going to call the predict method so that it tells us which classes it's going to predict for each of these examples. And now we're going to give it all the examples in our training set. So we are going to predict the training examples and the validation examples all in one line here. The errors will correspond to all of those cases where the predictions are not equal to the class. So if the logistic regression is predicting one thing and the class is different, this is an error. So this gives us a Boolean vector with true on every example that was incorrectly classified. And you can do operations with Boolean vectors in NumPy because true counts as 1 and false counts as 0. So if we take the mean of the errors on the training indexes, this gives us the average or the fraction of incorrect examples in the training set. If we do the mean on the validation indexes, this is the fraction of incorrect examples on the validation set. Okay, so now we can test for different number of features in this range. We're going to start from the original 2 and end at 15. And now we can compute for all the folds using 10-fold cross-validation. We can split our data into a validation fold and all the training part, and we obtain the indexes here. We compute the fold using the calcfold function there, and this tells us the training error and the validation error for this particular fold with this number of features here. And now we add this over the different folds, and we can print the average training and validation error by dividing by the number of folds. So this could be, for example, for testing all the different features, the different number of features using cross-validation. So this would be the kind of things that would be happening with 2 features. We have clearly underfitting. You see the training and validation error are very similar, and our model cannot really adjust well to the data, so it's always giving us these linear separations that do not properly classify the data. As we start increasing the number of features that we are feeding into logistic regression, we start having more flexible discriminants here, and eventually we start having this effect where we have a low training error but an increasingly high validation error. So if we plot this, we can see here the underfitting stage where both of them have a high error, and then eventually we have a low number of errors on training, but we start increasing the error on the validation So we can use this to select the best model. In this case, it will be this one with 9 features, and we will use that one for our classifier. So after this selection, note that we are measuring here the average of different hypotheses. We still do not have our final classifier. But since now we know what the best number of features is to use, we can train the logistic regression with the whole training set and obtain the final hypothesis, which is this one here. So this would be using 9 features for the whole training set. And now we can run this on the test set and see what are the errors that we get on the test set and obtain an unbiased estimate of the true error for this final classifier. Okay, so basically what we do is we do our pre-processing first, shuffle, normalize, standardize, and so on. We reserve a test set for the end to get an unbiased estimate of the true error. And now we're going to do cross-validation on the training set. We partition the training set into a number of folds, and we do cross-validation to select, in this case, the best model. And now we're going to train. After we select the best model, we are going to train it using the complete training set, so we no longer consider these partitions. We train with all the training data, and we estimate the true error on the test set. Now, the reason for this is that even though cross-validation gives us an unbiased estimate of the true error, so each of these individual points is an unbiased estimate of the true error of the different models, what we can get on average when we train these models with this kind of data. When we take them all together and pick the smallest one on purpose, we are biasing the estimate because we are now increasing the odds that we pick the point that underestimates by chance the true error. So this is why we need the test set at the end, because if we don't have a test set, we will not have an unbiased estimate of the true error, since both training and validation have been used by us to decide and to optimize something. So to sum up, we saw the problem of classification. We need to separate the two classes, so it's not just fitting a line somewhere, but also distinguishing between what is on one side or the other, or eventually a hyperplane if it's in higher dimensions. We also saw that we can keep using linear models even if our data is not linearly separable, if we do those nonlinear transformations before. Now, we did this with logistic regression by hand just to illustrate the idea. In practice, there are other classifiers that are a lot more practical when you need to do nonlinear or to classify classes that are not linearly separable. We also saw how to evaluate the classifiers, and we saw this approach for solving or mitigating the overfitting problem. We can choose the best model for each situation by looking outside the training set to get an estimate of the true error of the model. However, when we use those estimates to select the best models, then those estimates are no longer unbiased, because every time you throw the dice a number of times and then pick the smallest or highest values, you are biasing those estimates. So we either need to split our data into 3 sets, train, validate, and test, so that we use one to train, the other to validate, to optimize all of these different decisions, like choosing the model and then testing. Or better yet, we use cross-validation. So with the training set, we iterate through different, leaving out a different partition at each time for validation. We average that, and we have a better estimate of how the model performs on that kind of data.